Hello and welcome to this Quintus Tech Talk. Today we're going to be talking with a couple of leading people in the AM world, Mr. Donald Godfrey from SLM Solutions and Andrew Westman from the University of Arizona. And we're going to be talking about F357, production using additive manufacturing, and then what can be done with the post-processing of the parts later on. So to start off with then, could we please just have a short introduction? Mr. Godfrey, could you say hello?
So thank you, Jim, for inviting me to this event. My name is Don Godfrey, and I am employed as the Global Director for Additive Manufacturing for Aviation and Defense. I spent 15 years at Honeywell Aerospace installing additive manufacturing systems across Europe, across North America, and Asia. Prior to that, I spent 11 years at Rolls-Royce Aerospace. At Honeywell, not only did we print components, but we got those components approved by EASA and the FAA for commercially available flight. I was able to work with universities around North America, top leading institutions. We authored a book titled The Technology, Materials, Design, and Production of Additive Manufacturing. And I've been fortunate enough to have been awarded over 40 patents in the area of AM. This is going to be an exciting talk. I look forward to it.
Perfect, thank you. And Professor Westman, can you give us an introduction as well?
Hi, Jim. Thanks for having me participate in this event. I'm Andrew Westman. I'm on the Faculty of Material Science and Engineering at the University of Arizona. Prior to coming here, I worked for the General Electric Company for 14 years, first in their aviation division, developing nickel superalloys for turbine engines, and then in GE Additive's business for creating materials for additive manufacturing.
Great. Well, thank you very much for both attending this talk today, and I'm looking forward to a very exciting discussion around the topic of F357. So what are the issues around that? You want to give us some comments, Andrew?
Yeah, there's a number of different issues around aluminum F357 that industrial users need to be aware of. First, it's a alloy that's from the casting industry originally. And so a lot of the heat treatment practices have been designed for cast parts, typically some larger structural castings. So the common practice for heat treating it involves a solution heat treatment and then a water quench as part of the T6 temper. This water quenching process can cause issues like distortion, that can be especially pronounced in thin, near-net shape additively manufactured parts. F357, when processed in additive manufacturing, also tends to absorb dissolved gas, probably hydrogen from water vapor exposures, either as the powder or during heat treatment processes. And after a high temperature, high pressure heat treatment like hot isostatic pressing, the dissolved gases can come out in later processes when that pressure is released. So you can have a part that looks good after a HIP process that then forms what we call blisters on the surface of the parts during the subsequent solution heat treatment or aging processes.
Right, so you see hot isostatic pressing as a way of combating this, or?
I think hot isostatic pressing is certainly a way to combat this, but it also gives us some unique opportunities with what Quintus is doing to combine HIP and solution to limit the thermal exposure the part is going to see at lower pressure to just the aging process, which occurs at lower temperatures. And that should provide us a benefit to avoid the blistering. The other issue is that the users out there have been typically avoiding the blistering issue by simply avoiding high temperature heat treatments, avoiding the solution heat treatment and age process altogether, and just using an as stress relief condition. In doing that, they're trading away a lot of the yield strength capability of the material. And so while you can avoid blistering by choosing to stick with a lower processing temperature, oftentimes that leaves you with worse mechanical properties. And so we're looking at ways to get everything that we want from the alloy, good mechanical properties, low distortion, and no blistering.
Right. So in the work you've been conducting with us and SLM Solutions, you see that there's a benefit to a new process route then. So Donald, can you tell us a little bit about what you see happening in the industry around aluminium alloys today?
Aluminum, the two dominant aluminum alloys is AlSi10Mg and F357. AlSi10Mg came on the market because, to be honest, it was introduced by EOS. F357 came on the market because it was pushed by GE Aviation. Now, when you look at aviation, they have centered around those two alloys simply because they're weldable and we're beginning to gain some understanding of how well they perform. The problem with these additive alloys, so for example, if you have a casting, it cools maybe in 30 minutes, right? And you take it out of its shell or out of the sand. But if you have a printed part, it cools at a rate of 10 to the minus 6, right? It's so fast. It's so fast that the microstructures are very small compared to a casting that has components with elongated grain structures. So when you take that aluminum that's been printed and you put it in a water quench, it distorts uncontrollably. You cannot control it. And this is a problem. And to get around that, some companies will only print and stress relieve. Some companies will refuse to HIP. Some companies will stress relieve and HIP only. And when they do that, they do not get the true mechanical strengths that they want or need, so they don't use it. And now we're trying to go into using what might be referred to as a direct age. Because aluminum is so hard to use, a lot of different companies do a lot of different things. There hasn't been a standardized way to get around these problems. And that's why it's so important to work with brilliant people at the University of Arizona to help us solve this problem, not just for SLM customers, really for the whole global additive manufacturing community.
Yeah, and that's a great segue into what we're talking about here now. So Andrew, I mean, what have we been doing with you? We've been working with our patented technology around uniform rapid quenching, URQ, which is used to cool extremely quickly from the HIP temperature and pressure. How have you been using that?
So what we wanted to learn in using your technology is whether we could achieve the mechanical properties we were looking for by quenching quickly enough to suppress the formation of the precipitates in F357 and then age them to get the optimal yield strength. This is the typical process for a T6 temper in these types of alloys. If you're not able to cool quick enough, you get enough precipitation and growth of the precipitates during the cooling process that you've already passed the peak strength of the alloy before you have a chance to properly develop the precipitation during age. So a fairly rapid quench in these types of alloys is critical to getting the mechanical properties. And that's not typically been something that's been achievable in the HIP process. So we've always in the past had to do a separate HIP and then a solution heat treatment where we're just really trying to reheat to a similar temperature, but dissolve the precipitates and then quench them into a fine enough distribution at a rapid cooling rate that we get the mechanical properties we need.
Right, so you've been running different HIP trials with us now in our application center in Columbus, Ohio, using quenching technology basically at different HIP temperatures, and you've been looking at aging as well. So what kind of things have you come up with here?
So what we really wanted to try were a couple of different variables, and we designed an experiment to look at different hold temperatures and different pressures during the HIP process. And then we just said, let's quench these things as quickly as we can within the HIP vessel. So we ran an experiment and then some baseline samples with the standard water quench and relief only that we're seeing used in industry. And then we did tensile testing to see what the results were. And what we found is that the results from the ultra rapid quench process were pretty good. They were very close to what we were seeing in our baseline water quench samples, and they certainly exceeded the benchmark values for F357 that we see in the MMPDS materials handbook. So it was a fairly positive result that we saw when we made these trials. And then we decided we would repeat a few different conditions to see how robust that was.
Right, so the yield strength you were seeing, they were pretty consistent and very good, right?
Yeah, they were very good. So what we found was that the results for our higher temperature point were the best. They at 530 C HIP hold temperatures, followed by rapid quench, we were able to get yield strengths that were approaching what we were seeing for the water quench material. If we went down to our lower hold temperature at 500 C, we did trade away a few megapascals of yield strength, but still were able to exceed the benchmark values in MMPDS. The pressure in this case did not seem to make a significant difference to the yield strength results.
But what about the elongation? Did you see any significant changes there?
All the elongation values in that experiment were above 15%, so I would say that they were all very good for an aluminum alloy, where you expect to have some trade-off usually with yield strength and ductility.
So on the whole, very positive results then. But what about the blistering that you mentioned earlier? Do you see any effects of doing this in a different way to the standard production method?
I saw no blistering, Jim. So
right.
I'd say from that standpoint, it looked very good.
And as we've gone around the nation talking to customers, it's very, very difficult to really put your finger on where the blistering comes from. And some companies will tell you that it's hydrogen or moisture attached to the powder. Some will tell you that it's moisture in the machine. One company that I respect a lot did an experiment where they printed X number of bars and split those bars into 2 batches and sent one batch to a heat treater A and another batch to heat treater B. And heat treater A came back with blisters and heat treater B did not. And that tells us that it's moisture in the furnace. It's moisture in the furnace. So, and this is a real problem. Blistering is a real problem. And it's tough to get a hold of and conquer it when you're dealing with aluminums because there's so many opportunities for contamination. But this technology that was led by Andrew proves, I think, that if you have good manufacturing processes that are under control and a good operator on your heat treater, you can beat this thing.
Right. So, but using quenching in the HIP, I guess you're under pressure, so you're stopping the blistering happening anyway.
That's right.
Yeah. That's a really interesting. But I mean, we're quenching the material in the HIP here. So how does that affect like the tolerances on the material, or the quenching is always associated with distortion of material. So what results have you seen there?
The results from a dimensional study that our partners at Honeywell Aerospace conducted were also very positive. We did not notice any significant distortion from the quench after the HIP process in the URQ system. They ran a couple of trial parts and measured distortion values at some representative locations and found values that were more in line with stress relief only or HIP only processes, and much, much lower than what they were observing in water quench. So obviously distortion is a measurement that has to be taken in the context of the customer's needs. And the feedback we received from Honeywell was that this would meet their needs. So that's really a win for them.
That sounds very promising, yeah? So we're able to control obviously the porosity with the HIP. Using the quench, we can get the right microstructure, and we can avoid the growth of pores and avoid blistering. And at the same time, the tolerances are within the realms of what are normally seen. So do you see a future for this technology? Where are we going?
From my perspective, I think there's a lot of promise in this process for optimizing for a number of different priorities for aluminum alloys. You can get the properties you're looking for while avoiding issues around blistering and distortion. So from my perspective, I think it does have a lot of promise going forward. I think that the customers would be interested in this sort of technology for a wide range of parts, especially in aerospace.
So you see an opportunity for a robust industrial process here with multiple laser machines and getting results that are predictable.
I do, and that goes along with a little bit of what we did in our FollowOn experiments with Quintus, where we ran not just a set of new make 30 micron test specimens we had been using from SLM solutions, but also ran a set of specimens where they had increased the layer thickness to 60 microns. And in those specimens, we still saw that SLM was able to deliver test material to us with full density and high quality in the as-built condition, and we saw no development of porosity and equivalent mechanical properties for those 60 micron specimens as well. And increasing those layer thicknesses without seeing any issues has been a big challenge. So that's another positive result for the process robustness. Another thing we did was we had some test bars that had been mistakenly solution heat treated rather than stress relieved. And we wanted to recover these test bars for some additional work, but we're unsure if we could safely reheat treat these parts and get equivalent properties. And we found that with this process, we were able to do that, which makes sense. If you're solution heat treating something, you should see an ability to dissolve and then reset that microstructure with the solution heat treatment process. But it doesn't always work out as planned. Sometimes you'll get differences because of the different thermal cycles. You might incorporate some of that gas and see a blistering issue, or you might get uncontrolled grain growth or other issues like that pop up. So it was really an interesting result that reheat treating these test specimens after a mistaken high temperature cycle was able to recover the properties we were looking for.
So, but it sounds like you've got a couple of really interesting areas here. One is saving parts that might be scrapped otherwise. And the other area here is the ability to maybe change your printer parameters and get up the speeds with a multiple laser system and get very, very good results out of the printer. So Donald, I mean, what's being done now on these large pieces of equipment to get the properties out of the machine that can be really generating reliable, robust parts after the hipping process?
Mm-hmm. So when companies begin to move from laboratory additive manufacturing to production additive manufacturing, like anything, time is of essence. And the industry has moved from 20 and 30 micron layer thicknesses to now we're printing with customers at 60 micron, and we're in development with 2 customers to print aluminum at 90 micron. Now you can go higher thickness, thicker layers, but you still have the requirement of meeting design intent. And the regulatory agencies require that we have the burden of creating performance-based data that says we can do it repeatedly over time. And that's why these experiments that we're doing here with the University of Arizona is so very, very important. And we're also doing it with NASA, and we're doing it with NIST, we're doing it with other government third-party agencies. You know, and we're putting our reputation on the line. If these things crash and burn, Andrew is required to tell the truth, right? He's going to tell you what they are. But we have empirical data to show that 60 microns produces the same material properties as 30 microns. And the other issue, as our machines get bigger and bigger, you're going to have multiple lasers being used to print one part. We have to show through empirical data, through performance-based data, that using multiple lasers does not hinder the mechanical properties of anything that you print. And you're going to see that, right? And I think the other element that's so very, very important about this, it's kind of a side element, but it's reality, right? You send parts out to be heat treated. They're not going to be heat treated correctly each and every time. They're just not. And so we took some aluminum that was misheat treated, we brought it back to its original state, and we took it to design intent. That is critical. That is a major step, because in the 35, 40 years I've been working with metals, what we would always do is throw it in a trash can. It goes to MRB, somebody signs off on it, and you throw it in the can. But you don't have to do that with this new technology, and it would save companies months of manufacturing time.
So you actually see a change then in the possible layout of the production setup to actually produce these parts by shortening things and maybe avoiding different heat treatment steps and actually doing everything in the hip?
Yeah, so if you can do the hip and the solution in the same cycle, it saves so much time. It just even in unpacking and packing and shipping to a heat treater, there's 3 days right there, right? It's you trade 30 minutes for 3 days. It's a big deal.
So what we can see here is, I mean, we get some fantastic microstructures out of this as well then, Andrew. So what would you say about the microstructures that you see out of this material, the grain size and the way the material looks?
So one thing that was interesting that we observed was that using a single cycle that combines the HIP and solution heat treatment creates a finer distribution of the eutectic silicon particles within the aluminum alloy. And this probably has a little bit of a benefit in terms of the consistency of the yield strength that you're going to get from this product. I'd say we have a lot more to do in looking at the microstructures of these materials, and so we're excited to keep working on this program, but our initial looks at this were very positive, and we didn't see any porosity, we didn't see any unexpected non-metallic inclusions or things like that would give us any cause for concern. So overall, I think the shorter cycle time has a microstructural benefit as well. And we're going to spend some time understanding that in some more detail.
So on the whole, it looks like a fantastic development. I mean, what's your take, the two of you, to kind of round off here now? What's the take on the study that we've done together now? I mean, how is this going to affect the world now?
As a scientist, I really think there's some exciting things we can look into in a lot more detail. But as an engineer, I feel like we've really found an excellent engineering solution for a practical problem that is impacting the additive manufacturing industry for aluminum today. So that's got me very excited about the possibilities for looking at this in not only in F357, but for other aluminum alloys and for other alloy systems going forward. I think it's a great technology that has a lot of potential and a lot of really interesting research directions that we can contribute in.
What I envision is that there will be a considerable amount of interest in the North American space, aerospace, defense industry to look at this technology. And there will be a lot of communications between those companies, SLM, the University of Arizona, and Quintus. One major company is already aware of what we're doing and communicating with Andrew. And it does not mean that they are going to change what they're doing in the next 30 or 60 days. But communication has started. And I envision programs coming down the road to ask Andrew to go qualify 500 or 1,000 specimens, and they'll make a decision on how they're going to move forward. But Andrew's work is being noticed. And with this video, the whole world's going to see what he's done.
And it's excellent. I mean, and that leads me into another thing, which I think is really important. I'm guessing, Andrew, this is going to be published, right? So when's it going to be available for people to read?
Yeah, so there's a white paper we're currently working on to take a lot of the results we have so far and put them in a form where you can reach out to your customers and give them the engineering knowledge that they need to know about what this process can do. But what I would really like to also develop is a lot of the scientific knowledge around how these microstructures develop as a function of this thermal history and what that means for the mechanical behavior of the material. And we're getting close to having that wrapped up. We still have a little bit of work left to do, but I'd like to have a journal article out there probably by the summer that can give a lot more of the finer details that can help to explain to people what's really going on in the material itself. And I think that deeper scientific knowledge is a key component of building the comfort level of what is a very sophisticated customer base for this technology. They don't want to just see that you have an engineering solution. They want to know why it works. And I think we can do a great amount of work and publish that by the summer. And then keep going on this. I think like I said, there's a great amount of interesting science that can be done looking at the effects of temperature and pressure and the overall process. And we intend to keep going with that and would love to partner with people that are looking to understand this process at a deep level and use that deep knowledge to then create additional robust solutions to more engineering problems.
It sounds excellent. So by Q3 2022, it's going to be out there. That's what we can say.
That's the goal.
That's the goal, yeah. Well, that's fantastic. So I'd like to thank both of you, Donald and Andrew, for your time today. It's been great having a discussion about your work that's ongoing and how we've been able to support you on this technology. I think the quenching technology in the HIP, the URQ technology for us is a key piece of IP. It's great to see it being used in reality and showing such great results. So I leave the word to you guys to say just a few words at the end of the discussion here as well.
I appreciate you having me on to speak with you today, and it's been great to be a partner with you and Chad Beamer at your North American Application Center. You guys have been great partners with us, and we look forward to working with you on a lot more interesting technology in the future.
And SLM is very pleased to partner with universities like University of Arizona, particularly Andrew. It's kind of fun for me because I live up the street. I just get in the car and I can drive down and see what he's doing and talk with his team. But we are a company that that not only manufactures 3D printing machines, we're becoming a company that partners with leading aerospace and defense giants, and we want to be part of problem solutions. We want to solve your problems using additive manufacturing technology and subsequent technologies that go along with that. So a lot of partnerships. We partner with some brilliant people like the researchers at Quintus and Andrew and his staff. It's just so much fun. It makes coming to work fun.
Excellent. And coming to work when we're happy is great. And of course, we're not only working with aluminium alloys, we're working on a host of different stuff as well together. But this little talk's about F357. Fantastic work you guys have done, and thank you very much for participating today. And looking forward to the next Tech Talk when it comes up. Thank you very much.
Thank you.
Thank you.